for this. Thank you for this opportunity. So this talk is about the gliding flight of Alsomitra macrocarpa, also known as Javan cucumber, and other seeds like Taraxacum officinale, commonly known as Dandelion, and Zelkova belisia. I'm quite sure that you don't know Zelkova and you are not familiar with Alsomitra. I studied these seeds for different reasons during my time in Edinburgh. And my work has been guided and supported by my supervisor, Dr. Cummings, Giorgio Serchi, Enrico Mastropaolo, Dr. Nakayama, and Professor Viola, and also other researchers that I had the chance to meet and work with, like Dr. Tani, Dr. Young, and Professor Kozlowski. So, first of all, when we talk about seeds, usually one of the first tests performed to understand something about the seed is the drop test. And the idea of a drop test to let an object, or in our case, a seed, fall or glide in quiescent fluid is an old concept. I'm from Tuscany, and I studied at the University of Pisa. At the end of the 16th century, Galileo Galilei, professor of mathematics at the University of Pisa, is said to have dropped different masses from the Leaning Tower, pictured here, to demonstrate that their time of descent was independent of their mass. So if we had been inspired, we could have performed the drop test for our seeds, Dandelion, Alsomitra, and Zelkova from the Scott Monument in Edinburgh. So now, being serious and focused, let's start with the dandelion. So you have probably come across a dandelion. Maybe you have some yellow flowers that are growing in your garden, or you have spotted it growing in the cracks in the pavement. But for this talk, I'd like to focus your attention here. Sometimes people blow the fruit of the dandelion plant and make a wish. So in the red frame, we have the fruit of the dandelion. First of all, just a little bit of terminology so that we are all on the same page. A dandelion, starting from the bottom, as an achene, commonly named the seed, which is the payload. Then there's a stalk that connects the center of mass, because 80% of the mass is concentrated in the achene, to the pappus. The pappus is this parachute made of individual filaments that are connected in the pulvinus. So first of all, we took some measurements, and here in the black image, you can see a CT scan of a gold-coated dandelion. This kind of tool allowed to measure, for example, the diameter of the filaments, and we will soon see why it matters. On average, 16 micrometers. The length of the filaments, around 7.5 millimeters. So the mass is 610 micrograms, and this is the lightest seed that I will present today. And it has a terminal velocity. So after the transient, after the release, when the drug balances the weight of around 27 centimeters. Last but not least, the pappus, the parachute, is made of around 100 filaments. So talking about the physics of the dandelion, how the seed fall, when the seed falls from the parent plant, it accelerates and then reaches the terminal velocity. The fluid flow builds forces in, if we are looking at the left drawing, in the normal and tangential direction of the filaments. At terminal velocity, the forces acting on the filament altogether will balance the weight. In the commonly accepted model, the forces on the filaments are added up, and this gives the total drag that balances the weight. On the opposite side of the possible models for the pappus, there's what we have on the right, so a simply solid disc. In this case, we would think that the filaments behave like a solid membrane. And to explore these possibilities, we performed a simple drop test with several dandelions and several technical repeats. So this one was the very simple setup that we used in Edinburgh. So to test this hypothesis, the setup was made of a camera that was looking at the plane where the dandelion was falling. Recording the motion of a dandelion is quite trivial, given that it's in quiescent fluid, it's a 1D motion. So then we had a black background, helpful for the algorithm that was detecting the motion, a hot wire anemometer to check that the fluid was still, and a calibration chart used to connect peaks and physical lengths in the image. So the tracking was quite trivial. On the left, we have two snapshots of two frames. And basically, with the threshold on the pixels, the images were recorded in black and white. And the dandelion, when illuminated, is basically a ball of white light. So the algorithm was tracking the centroid of the white pixels, the pixels that were below a threshold. And then because the dandelion is quite stable and performs basically a 1D motion at constant velocity, on the right, I added a very trivial plot of the vertical component of velocity, the only component basically, because there's no motion on the perpendicular plane in time. And this one allowed to get the velocities. So if we were to plot the terminal velocity against the disk loading, that is the ratio of the weight over the projected area, the area given by a flattened pulvinus, the set of filaments. Here we have 10 different dandelions with 10 technical repeats each. So this one is the best fit. This one is what would happen if we had individual filaments providing the drug. So in that case, we would be in Stokes flow conditions because the reference length would be the diameter of the filament, and the Reynolds number would be well below 1, around 0.25. And so we would have a linear dependence of drag on velocity, and we could find the linear dependence of velocity on the disk loading. And as we can see, This fitting is far from ideal. The other case is the impervious disk, where we have a square root dependence of velocity with the disk loading. This one is closer, but still not, it doesn't match the data that we have. So this one led us to a conclusion that the physical behavior of this filamentous parachute was a behavior given by something in the middle, not a solid disk, not a membrane made by individual filaments. So in the end, my supervisors picked up a porous disk. And here I'm summarizing basically those results. So the Dandelion, Papus, sorry, is a porous disk. The other seed that I studied in a side project was Zerkova bellicia, and the connection with what brought us to Zerkova bellicia is completely different from fluid mechanics or other connected fields like robotics. So Zerkova bellicia is a relict species that grows on the island of Crete. It's threatened by overgrazing, browsing of animals, soil erosion, drought, and fires. And it ended up on the endangered, on the list of endangered species listed by the United Nations. And while the dandelion is a pappus seed that falls in an almost one-dimensional fall, Zerkova bellicia disperses a twig with fruits and leaves attached. As we can see here, 3 leaves and 2 fruits. So, again, we recorded several dimensions, but here I'm listing the most important for this kind of presentation. So we randomly selected 32 naturally detached dispersal units of Zerkova bellicia, and these were carrying 27 single fruits and 126 leaves. So the question is, for instance, why is Zerkova dropping a twig? This one is quite unique in the biological world, to drop the fruit with the leaves. What's the advantage in terms of, for example, seed dispersal, if there's an advantage? So just to give you an idea, the mass is 67 milligrams, so orders of magnitude higher than the dandelion. We have a diameter also of around 38 millimeters, surface, and the terminal velocity that is, in both cases, both for the dispersal unit and the fruit, 1 order of magnitude higher than the one of the dandelion, and the Reynolds number of 500 for a fruit and 4,000 for a dispersal unit. So why this unique dispersal technique? So is there an advantage to disperse a dispersal unit, so leaves and fruit, instead of a single fruit? And given that Zerkova is a relict species, which means that millions of years ago, this branch of the family Zerkova was isolated in Crete, while the others developed in Southeast Asia. Is there a connection, or these two branches of family Zerkova developed independently, also because they were growing in totally different environments, in totally different conditions. And what is the flight mode of the dispersal units? So this one is a falling dispersal units that we modeled as a solid disk. So with the drag coefficient of 1.18 and the terminal velocity. And as we can see, the falling motion is characterized by a random motion. So we have the dispersal units, moving left to right, tumbling and doing all kinds of motion, while the individual seed, the noise comes up in the video, yes, performs a perfectly one-dimensional motion. And this one instead was modeled as a rough sphere, looking at the work of Haider et al. On the motion of sediments and other pieces of rock that comes from volcanoes. So the falling velocity of individual fruits is almost twice that of dispersal units, and this one is quite trivial. Also, individual fruits fall in a straight path, in a perfectly one-dimensional motion, like a stone, they fall to the ground. And there's no horizontal motion. So basically, they start their fall and they land at the same side. So single fruits were reasonably modeled as non-spherical shape with the sphericity psi reported here, pi d squared divided by SA. So the dry leaves act as a drag enhancing appendage that increases the surface area more than the total mass. So in the interplay, they enhance drag more than weight. So going on, we basically plotted the horizontal distance traveled over 1 meter drop by the dispersal units that we had. And what we found was that there's basically no dispersal of this Zelkova bellicia that is suffering in Crete. And here, if we have a quick look, basically we can see that in this plot where we group pappus seeds like the Dandelion, for example, gliding seed like Alsomitra macrocarpa that has a terminal velocity similar to the terminal velocity of a pappus seed, even if the wing loading, so the ratio of weight over surface is orders of magnitude higher, and Zelkova, both as dispersal units and individual fruits, are grouped far away. So we concluded that there was no advantage and no inclination for seed dispersal in Zelkova. So what we found was two dispersal modes: slowly falling dispersal units in chaotic path and fast falling fruits in a straight path. Interestingly, the dispersal mechanism is the same of the East Asiatic Zelkova. So even if they were separated millions of years ago and they grew up in totally different environment, they kept the same dispersal mechanism with the twig and individual fruit, and the dispersal is quite limited. And for that reason, as you can see here in this picture, the most effective way to protect Zelkova is with fences. So this is, given that Zelkova is not able to populate areas where animals might not be able to go, the best way to save Zelkova is to close the areas where it's growing. And then we have Alsomitra macrocarpa. So Alsomitra macrocarpa is the last but not least. It's known as Javan cucumber. And so this one is a plant that belongs to Southeast Asia, can reach up to 50 meters in length. It belongs to the family of cucumbers. So basically you have to imagine a liana that grows around a tree. And when it finds a branch, it grows around the branch, and then it hangs a coconut with 400 of these seeds, basically. And then when there's a slight breeze and the fruits are ripe, they fall and glide over the forest canopy. It grows in the Malay archipelago, and the glider, as we can see in the image on the left side, is made of two parts, basically. A seed containing pericarp of brown color placed near the leading edge and centered on the longitudinal axis. That one could be considered a plane of symmetry, with the circular shape of 2 to 3 centimeters in diameter. And this is where the center of mass is located. So we verified this one with the simple test balancing Alsomitra on a rod 4 millimeters in diameter. And then there's a membrane wing, which is much of the surface, with a wingspan of around 17 centimeters, as we can see. A total wing surface of 10,000 square millimeters, and the mass as little as 0.36 grams. The average density, to give you an idea of Alsomitra macrocarpa, is close to that of common tracing paper. And as we will see, the fact that it's so thin and so light that is basically transparent is a problem for tracking. So, first of all, a simple question: what makes Alsomitra macrocarpa so special and other than the unique shape? So for sure, it's an unusual shape for a seed. It's basically a seed containing pericarp moved around by this membrane wing. So Alsomitra does not rely on wind to disperse gas and updrafts to cover distances up to hundreds of meters. So it simply falls from the tree up to 50 meters high and glides. It has the highest descent time, where the descent time is defined as the square root of the density times the descent factor divided by 2 times the wing loading. So rho is the density of the fluid, dF is the descent factor, and the descent factor, as we can see here, is 1 plus horizontal velocity divided by W squared times lift coefficient. So the descent factor in the end gives an indication of the aerodynamic efficacy. And the plot that we can see here highlights how Alsomitra macrocarpa, which in this case is the red diamond in the top left corner, is far from the average. It is a specialized gliding seed. Here in the rest of the plot, we have auto-rotating seeds like the maple seed. And we also have strain seeds and gliding seeds with the red square. The dandelion, for comparison, is this green star. So even if they have low wing loading, they present a very high descent time with two completely different geometries. So just to have a quick break, I wanted to show you the gliding flight of Alsomitra. So most of Alsomitra macrocarpa perform a helical flight, as we can see in the video on the left, while the remaining 20% does straight gliding. And this is quite common in the world of seed dispersal. For example, if we think about the dandelion mentioned before, 90% of dandelions or even more fall 2 meters or less far from the mother plant. And this one is still an open debate, the biological reason why this happens. So we wanted to track the motion of Alsomitra, and we thought that cameras like the Azure Kinect, which is a depth camera, could be a good option. But because the Azure Kinect camera, depth camera, works with the technology times of flight, so it shines, in order to collect the third dimension, the depth, it shines an infrared light at a specific frequency, and then it, when it gets the signal back, by knowing the speed and the time taken to go and come back, it gets the third coordinate. We needed to know that the material of Alsomitra macrocarpa was able to reflect properly the wavelength of the infrared light emitted by the camera. So we did some tests at King's College London with the spectrometer to understand the emissions of the seed-containing pericarp. So here on the horizontal axis, we basically have the wavelength of incident light. And if we look at 850, which is the wavelength emitted by the infrared sensor on the Azure Kinect camera, in the plot on the left, we have the reflection spectrum. Basically, it's the wavelength of reflected light on the vertical axis versus the wavelength of the incident emitted light by the sensor on the horizontal axis. On both axes, we have a range between 600 and 900 nanometers, and the color map represents the intensity of the detected light. So we wanted to make sure that the material, the biological material of Alsomitra macrocarpa was able to reflect the light at that specific frequency, but also with a certain intensity. So if we take a slice of this plot, we get this plot, the 2D plot. And this 2D plot is basically a slice at 850 nanometers, and we see the peak. So basically this plot is obtained extracting the values from the 3D plot on the left, when the incident light is at a frequency of 850 nanometers, which is the frequency at which the infrared sensor of the Azure Kinect camera operates. So when the seed-containing pericarp, in this case, or the membrane wing, as we will see soon, are illuminated with the light at 850 nanometers, which is what we needed, they reflect at 850 nanometers. If they were absorbing all the incident light, or the reflection was not as intense as it is, there would not have been peaks, no detection of Alsomitra macrocarpa being possible. And this one is the plot for the membrane wing that gives a stronger reflection. So, challenges regarding the tracking of Alsomitra macrocarpa. So the biggest limitation is that the maximum frequency at which the Azure Kinect cameras operate is 30 Hertz, which is luckily enough for Alsomitra macrocarpa that glides basically moving at low frequencies. Given that the highest frequency that we detected in the motion was 10 Hertz, that was okay, but we were lucky from this perspective. The object that is imaged with the camera must be between 0.5 and 3.86 meters in order to be detected. The camera is very sensitive to light conditions in the environment, and Alsomitra macrocarpa, as was probably visible, has a wrinkled membrane. It's not a flat, smooth surface, but as a wrinkled membrane that affects the direction of the infrared signal that is reflected. And Alsomitra is also partially transparent. This one is another issue, not that we also experienced when doing PIV in the wind tunnel. And from the setup design, the non-uniform background was a problem. So this one was the setup that we built, and it's simply made of two Azure Kinect cameras that we can see here pointing to the ground. So we tried to place the cameras in a position where the gliding seat could present the highest surface to the camera to maximize the reflection. We had 3 soft boxes to keep the light conditions as uniform as possible in the volume that we were looking at and throughout the day. Then we had the robo arm with an electromagnet. So here you can see a metal disc. Basically, when the current was cut to the electromagnet, the disc was falling and it was releasing Alsomitra macrocarpa. All was done to operate the experimental setup from far away and minimize basically and keep the air as still as possible. Then we had the black background that turned out to be the most effective, and computers to operate the cameras and the robotic arm. So just a very quick block diagram to highlight the algorithm to process the data collected from the cameras. So first of all, there's the acquisition of the point cloud from the depth cameras that have a reference system linked to them. Then we were merging the point clouds belonging to the 2 cameras, thanks to a calibration done before starting the experiment. Then perform geometrical transformations to be sure that the black background that was lying flat in the setup was flat and overlapping with the X and Y axis of the inertial reference system linked to the laboratory. Then align the point cloud to the laboratory reference frame, define a region of interest, and clean and denoise the region of interest. In the end, extract the centroid of the point cloud. So Okay, so here we have, first of all, the transformed point cloud, and with the red line, I highlighted basically the sections coming from the two cameras. So camera 1 and camera 2, we had an overlap volume to try and have a continuous description of the glide of Alsomitra macrocarpa. And in the yellow circle, you can see the point cloud that comes from the gliding seed at this specific frame. Then the following slide shows the definition of the region of interest, the ROI. So the reason behind the definition of the region of interest were because we wanted to have only the gliding seed inside of it, and also by limiting the volume investigated, and as a consequence, the points in the volume investigated, we were able to reduce the size and the load on the computer in terms of data. So by doing this, we could move from 100,000 points to simply 2,000 points of the point cloud that was of interest. And then there was the most delicate bit of the processing, the denoising of the point cloud. So here on the left, we have a point cloud with all the points. And in the zoom in rectangle, there's in gray the full point cloud that was in the region of interest. And in red, overlapped, there's the point cloud, the denoised point cloud. So technically, by denoising the point cloud, we want to be able to remove the noise. So the cameras tend to add noise at the edges of the imaged object, where basically they get kind of confused, and because at the edge they don't know if the imaged point belongs to the object or to the background, they end up putting these points basically in the air between the object that you are imaging and the background. And on the right, basically, I plotted with the red circle, the original point cloud at each frame, and with the blue dot, the denoised point cloud. So ideally, instead of keeping the shape that we have with the raw point cloud, we would have like a constant number of points throughout the frames. Instead, I didn't manage to do it. So by denoising the point cloud, I was able to remove some of the noise, but the point clouds that presented more points kept more points and more noise than the ones that had fewer points. And here, basically, there's one of the results. So we started with the Dandelion that performed a one-dimensional motion. We moved to Zelkova that with the dispersal unit presented the planar motion. And here we have Alsomitra that went, so the Alsomitra, for example, in this case that flies straight, has a three-dimensional motion. So we were surprised to find out that even if it flies straight, it presents oscillation in the lateral direction. And here we have basically on the right with the black circles is the position of the centroid. So in the end, we ended up taking the centroid of the denoised point cloud for every frame, and then we fitted the function through it to give a kind of continuous description of the motion. So from there, we were able to extract the position, velocity, and acceleration of this body. This is still work in progress, and probably there are improvements that can be done. So the biggest disappointment was that when we processed the data, we found out that even if the point clouds were rich enough in terms of points with the description that was of more than 500 points, we were not able to capture the deformation. So we know that under the forces that Alsomitra experiences during the glide that change with time because it's not a steady motion, Alsomitra macrocarpa deforms, as we can see here in this image, in this picture taken during experiments in the wind tunnel. And the deformation is significant because if we look, for example, at the plots on the right, these are plots for different angles of attack for left and right tip that deforms differently and with different velocities, and the deformation has a minimum of let's say 2 millimeters at the tip and goes up to 10. So from this perspective, we failed to capture the deformed shape of Alsomitra macrocarpa. So to summarize, the tracking with the depth cameras gave good results, and the cameras allowed to sample a large volume. The advantage of depth cameras is this ability with just one camera to sample a wide volume, and this one is useful when you have different samples. For example, in the case of Alsomitra, we had 32 different Alsomitra macrocarpas that are needed in order to sample a population that is statistically significant, but it also means that every seed will fly in a different way. So you need to be able to have a large domain of investigation. The problem for sure is the limit on the frame rate. The cameras work well without markers, so this one was the main reason why we picked the Azure Kinect cameras. And for something like Alsomitra macrocarpa that is extremely light, 1/3 of a gram, and it has a flexibility that we didn't want to affect, working without markers is crucial. So the next step is to extract the Euler angles that describe the orientation in flight of what we are now modeling as a rigid body, and all the points of the denoised point cloud were projected on a plane, and put the information in a low order model to hopefully be able to capture this flight. Thank you.
Yes, thanks, Daniele, for this very nice talk. So we have 8 minutes for questions. So if you have any question, you can either post it in the chat, or you can ask unmute yourself and ask Daniele directly. So is there any question from the audience? So I guess I can start with a really big picture question. So Daniele, do you think that this kind of nature inspired design can be used in something like UAVs or like small drones, like rotor design? Will that like basically make an impact in the real engineering applications?
Definitely. And a few days ago, there was a paper published by a group at Imperial College where they used a platform similar to Alsomitra macrocarpa to carry around a sensor for humidity and other measurements. And also there's activity at smaller scales, for example, for Dandelion-inspired drones in my previous group with Professor Viola and Dr. Bose working on the Dandelion project. And there's for sure Alsomitra has dimensions that make it quicker to turn it into a drone. So there's not, in my opinion, much to do in terms of electronics. So you are probably able to buy off-the-shelf sensors that have the dimensions and the weight that can be carried around by a membrane wing like Alsomitra. Also, 80% of the weight is in the seed-containing pericarp, so the brown nut. And I'm sure that last year there was a paper on a drone inspired by Dandelion, and in that case the weight was milligrams. So 1/3 of a gram is a lot of material to play with. So I think that, yeah, it's definitely, in my opinion, the direction where things are going. And some seeds present more challenges, adapt the electronics to something like a Dandelion requires more effort than to adapt it to something like Alsomitra.
Interesting. And can we, a follow-up question is, can we scale this thing up? Like, can we make it something like maybe 10 times bigger? Will that still be able to have similar trajectory or those kind of things? Or?
Problem is that the fluid mechanics doesn't scale that well. So if you were to take a Dandelion and make it 10 times bigger, you then have the porous membrane behavior that you have at those small scales. So that was an advantage for us because the physics of the dandelion was there to be discovered, basically. If the physics had scaled up, maybe the discovery wouldn't have been there when we arrived. So yeah,
I see.
But it means that there's also much more to find out now that we are going towards those small scales.
Right. Yeah, I'm just interested, like basically in nature, we don't have that heavy seeds or anything, but I am just thinking that maybe we can basically inspire by nature and do something bigger scale and like deliver something heavier, like maybe use for some Amazon delivery, those kind of thing to deliver heavier packages. Yeah, definitely very, very interesting. Yeah, thanks. Oh, Giovanni has a question. Giovanni, do you want to unmute yourself and ask it yourself? Yep.
Hello, hi, Daniele.
Hi, Giovanni, we can hear you. Yep.
I have a question. One of early slides, I think it was slide 17 or 18. There was a diagram. Yeah, if you can go back, thank you. yeah, that's 18. So you say this is a graph of the number of units as a function of the horizontal distance.
Yes.
And this is basically centered over around 0 or something like that. So what do you mean with these negative distances? So I think it's kind of normalized distance. And if so, what is the reference distance?
So here, the negative distance, it's basically the motion. So the way it was recorded, it was the projection of the dropping point on the landing site was the 0.
Oh,
and
okay.
and then from there I recorded the distance. It was basically on a line because it does a planar motion. The distance from there, so positive, it means that
yeah, I see. So my question was based on what reference was 0. So 0 is basically the position, the final position of landing. Is correct?
The 0 is the projection of the starting point on the landing site. So if I was dropping it, so if you,
and so negative and positive are chosen based on what? So based on a given reference?
Left and right with respect to that.
Okay, so it's 1D. Okay, it's just 1D. Okay, thank you.
Yeah, it's 1D.
Okay, thank you.
I guess it's just the bigger the standard deviation is better from the nature standpoint of view, right? Yeah, very interesting. So any more questions from the audience? Okay, I guess if there's no more question, so please join me, and thanks, Daniele, for giving this very interesting talk. I really enjoy the videos, like showing how this seed falling in the air. So it's very, very interesting. Thanks for sharing this with us. And
for the opportunity.
Yeah, thank you. And if there's no more question, and sorry, Giovanni, are you trying to say something? Okay, so if there's no more question, let's thank Daniele again. And I guess we will resume our meeting next week at the same time. And take care, everybody. Yeah, see you next week. See you, Daniele. See you, Giovanni. Bye.